Welcome to Chapter 7, where we're going to be talking about the solutions to the Solow growth model. Remember, we set up the Solow growth model last week. It was really like a lot of equations that you saw. There was an equation for output, there was one for investment, and then there was the resource constraint. And we were trying to figure out, what the solutions were, right? So in this chapter, we're going to be going through and actually finding the solutions. Now, I say in the book, I probably should have made it just one chapter, but I didn't really want to bog you guys down, give you like this crazy long chapter that you have to read. I kind of wanted to break it up. So I guess I broke it up, and that's that. Can't really be fixed now. But anyways, let's go ahead and move on. All right. So, yeah, last time we set up the model and talked about what we would have to do to solve it all out. This time we're actually going to solve it out. I'm going to change it a little bit here. We're going to solve it graphically now and then analytically. Now, when I solve it analytically, you don't need to know how I solved it analytically. All that you're going to need to know are what the equations are, kind of what they mean, and how certain things interact with each other. Like if something goes up, what goes down kind of thing. And this is going to be the first of two parts to this chapter. The next lecture is obviously going to be the second part of this lecture. This lecture is mostly going to be graphical, math-related stuff. The next lecture is going to wrap up some of that math and the graphical, pictorial, whatever, and then tie in some economic intuition. We're going to learn about why these things work the way that they do. So we want to solve the model out, and we really want to know what the long-run behavior is going to be like. I mean, it's a long-run growth model, so of course we're going to want to know what the long-run behavior is like. When it comes to this long-run behavior, it's really going to be in terms of what it's trending towards and then how it's going to behave when there aren't any shocks hitting the system. So, we can sort of think of it as the system is going to be at rest. And when the system's at rest, what is it doing? All right, what is it? What's the long-run behavior of some of these endogenous variables? So we're going to solve it out with graphs. And we've got a couple of equations that we're going to want to graph, right? Because if you're going to graph something, you need to have some kind of a function to actually graph out. And there's really going to be three equations that we want to graph. There's going to be output, investment, and depreciation. So we've got output, which is the y equals a times k to the alpha. We have investment, which is a constant fraction of output, s times a times k to the alpha. And then we've got depreciation, which is delta times k. We graph all these out, and then we'll get to what the solutions are based on the graphs, but it's really, intersections of some things. So if we want to visualize it, here's output, right? This is just output as a function of capital. We've seen this ad nauseum at this point. You will continue to see it ad nauseum throughout the semester. Now, the next thing that we want to graph is investment. Now, remember, investment and savings are going to be equal when the economy is closed, meaning that whatever we save is equal to what we are investing. And we're saving a constant fraction of our income, which means that investment is equal to S, which is that constant fraction of how much we're saving, times our output, which is also our income. So since S is a constant fraction of income, right, it means that it's going to be somewhere on the 0-1 interval, inclusive. So if investment is equal to S times A times K to the alpha, then S times A times K to the alpha is going to be less than A times K to the alpha because it's scaling output down. Remember that, right? So investment can never exceed output because, well, it feeds into output. It can't exceed output. So investment will always be less than output, which means if we want to graph investment, it's going to be the same shape as output. It's just going to be scaled down by that amount S, which is positive but less than 1. So if I want to graph out investment, right, we've got output here. Investment is going to look just like output. It's just going to be scaled down. And in this case, it's also going to be blue instead of black. So all I'm doing is just scaling it down by some constant fraction, S. Now, if I want a solution, I'm going to be looking for a point of intersection. currently there's only one point of intersection. So, I mean, technically speaking, yeah, there's a solution, right? And it's when k equals 0 and y equals 0. But we want positive output values, not 0. So, I mean, technically speaking, yeah, this is a solution mathematically, right? If we were just going to stick purely with the mathematics, this is a viable solution. I mean, it satisfies the system. But economically, it's not a solution because we want a solution that's going to be making sense to us, right? Economic sense. And if we're talking about economic sense, we're probably going to need positive inputs. So when the capital stock's positive, output's going to be positive, and it's going to satisfy an assumption that we've implicitly imposed here, which is we'll need positive values for some of these endogenous variables in order to get positive levels of output. So we want a positive input of capital, which then gives us a positive output value. So we got to graph one more function in order to be able to get that point of intersection that we were talking about. And this is where we're going to be graphing out that depreciation line. It's going to be graphed out in red, so we've got everything sort of color-coded here so you can see and get an idea of what function is doing what, all that. Now remember, depreciation is the fraction of capital that depreciates times the amount of capital that we have at any point in time, say time t. So it's just the line delta times kt, right? Delta being the fraction of capital that's depreciating, k being the amount of capital that we have, delta times k. All right, so the slope of that depreciation line is going to be delta. What do I mean? Well, let's see. We got output, we have investment, boom, we've got depreciation. All right, so from these three graphs here, we can solve out the Solow growth model. But now it's kind of a question of like, okay, well, I see 2 points of intersection in the positive domain. So, well, which one is it? Well, it's really where we kind of got to think about some things here, right? Because, yeah, there are 2 points of intersection. One's correct, one's not. Now, we know that the economy is going to be saving a constant fraction of its income, right, output, which is equal to investment. And remember, investment's the flow in capital less depreciation. So is there a point, remember we want all the steady state stuff, things aren't really changing all that much, all that. Is there a point where investment doesn't change? Or put a little differently, is there a point where the amount the economy saves is perfectly offset by the amount at which capital depreciates? At that point, investment is equal to savings is equal to depreciation. What point is that? Well, it's the point where that red line, depreciation, intersects with the blue function, which is investment. When these two guys are equal, there's a level of the capital stock that makes the change in investment over time constant. This is what's known as steady state capital, and it's the amount of capital that the economy tends towards to achieve a dynamic equilibrium. Now, when a dynamical system is in a steady state, all variables are growing at a constant rate, meaning today's value of capital is going to be equal to tomorrow's value of capital is going to be equal to the day after tomorrow's value of capital, right? Any time period that we're looking at, if this is in a steady state, capital today is going to be equal to whatever that value of capital is at any point in the future. So KT equals KT plus 1 equals K with a little subscript SS for steady state. Now, capital's constant over time, right? So is investment, implying that there exists some steady state value for investment. And if investment and capital are both constant over time, there's going to be some value of output that exists such that output today, YT, equals output tomorrow, YT plus 1, equals steady state output, Y little subscript SS, for a steady state. So if we can get a steady state capital, we can get steady state investment. And if we can get steady state capital, we can also get steady state output. So we label the intersection point on the KT axis, KSS, which stands for steady state capital. Now, the next slide, we're going to have this graphed out, so you'll see what's going on. So when you're looking at this and you're looking at the notes and all that stuff, you might want to switch between these pages here. But the blue dotted line from steady state capital to the intersection point between depreciation and investment represents the steady state capital stock that makes investment grow at a constant rate. The value of capital, KSS, produces steady state investment, which is then labeled on the vertical axis. And since investment is a constant fraction of output, steady state investment is a constant fraction of steady state output. So we can graph it on the vertical axis. Steady state capital exists where investment and depreciation intersect. So looking at this graphically, it's going to be where red equals blue. And that's this right here. Right? So the depreciation line crosses the investment curve, right, where the red and the blue are equal to each other. The point on the horizontal axis that satisfies that is steady state capital. And the point on the vertical axis that satisfies it is steady state investment. Right? So steady state capital goes in, right? When capital is in its steady state, investment is also in its steady state, hence steady state investment. So far we have found steady state capital, and by default we've found steady state investment. But now we need steady state output. And if we recall, output is a function of capital, right? Capital goes in, output comes out. So it probably stands to reason that steady state output is also going to be a function of steady state capital. Which means steady state output is going to be achieved when we take steady state capital and we plug it into the function for output, which is then going to give us steady state output. So to find this point graphically, all I'm going to do is draw a vertical dotted line from the point that satisfies steady state capital, steady state investment, upwards until I touch the output function. Right? So this is steady state capital giving me steady state investment, right? And from that point of intersection, I'm just going to draw a line upward, and that's going to give me steady state output. So this right here is the solution to the Solow growth model, at least graphically speaking. Okay, well now we've found steady state capital, investment, and output. What about consumption? Well, this is where we got to go back to our resource constraint, y equals c plus I, right? We've got y, and we've got I, right? So all we need is c. And, of course, the resource constraint in the steady state is just YSS equals CSS plus ISS. So I'm going to draw some curly brackets, right? It's going to tell me the share of output that is invested, right? And it's going to be the vertical distance between YT equals 0 and YT equals ISS, right? And then if I were to get the vertical distance between Y equals 0 and Y equals YSS, well, that's going to be total output, right? What am I talking about? Well, all right, here's a little curly bracket thing for investment, right? So everything from the horizontal axis, KSS, up to the blue curve, that's going to be investment. That's how much of output is being invested. Because remember, the vertical value here is output. So the vertical value that goes from the k-axis up to I equals S times YT, the blue curve, right? That vertical distance is going to be the amount of output that gets invested every period. And the vertical distance from the k-axis all the way up to that black curve, output, right? That total distance is output. So if I've got output and I know investment, then that difference there between output and investment has to be consumption. Hence, I've got consumption right there in the curly brackets. Okay. So from here, this is the solution to the Solow growth model. And from this, we can play around with some stuff. We can change depreciation. We can change the amount that we're saving. We can impose technology shocks. We can say, the return to capital changes, all those things, right? We can play with that and really see the way the model works, which is what we'll be doing next week. Well, not next week, I guess Thursday of this week, where we understand some of the transitional dynamics, if there's an optimal savings point, things like that. But not today. What are we doing today? Well, for the rest of this lecture, we're going to solve it analytically. So you've seen it graphically. Now let's talk about what we did but like mathematically rather than graphically. So this is the stuff you don't need to know how to get these solutions. You need to know how to use these solutions. Right? So start off where we left off last week, right? A times k to the alpha equals c plus kt plus 1 minus 1 minus delta times kt. Remember, that's just the resource constraint with capital plugged in instead of investment and output. Right? A times k to the alpha is output, or so the left-hand side is y. The right-hand side, I've got c plus kt plus 1 minus delta times kt. Well, kt plus 1 minus 1 minus delta kt is investment. So I've got y equals c plus I. So that's my resource constraints. It's tying everything together. Now, doing the steady state stuff, put everything in the steady state. I just change any t or t plus 1 subscript with a little ss subscript. And I'm also, right now, just going to assume that A is equal to 1. So everything's in a steady state, and there's no source for economic growth, technological growth. Okay, what about the equation for savings? Well, if savings and investment are equal to each other, savings rate is bounded by 0 and 1, then it stands to reason that consumption is going to be 1 minus the savings rate times output, which consumption is equal to 1 minus s times kt to the alpha. Right? So remember, S times output, F of KT, is equal to investment. So KT plus 1 would be equal to S times output plus 1 minus delta times KT. What did I do? Well, I took investment. I moved it to the right-hand side of the investment equation, moved KT plus 1 to the left-hand side, and, well, that's what I got there. All right. So then I can plug in my Cobb-Douglas production function. Now I've got kt plus 1 equals s times k to the alpha plus 1 minus delta times kt. If I take equation 2, put it in the steady state for f of kt equals kt, which therefore would imply kt plus 1 equals kt equals kss, right? I get kss equals, and I don't know why I said f of kt equals kt. It's supposed to be kt plus 1 equals kt, which gives me kts, or kss, sorry. I got a little ahead of myself when I was typing up this stuff. Please ignore that part. Anyways, kss equals s times kss to the power of alpha plus 1 minus delta times kss. Well, all the k's are the same, right? Of course they are, because fixed points. We've found a fixed point at steady state capital. So we can divide both sides of equation 3 by steady state capital. Now I get 1 equals s times kss to the alpha minus 1, right, because exponents, plus 1 minus delta. Now I want to solve for kss, so I'm going to move that to the other side. All right, I'm going to subtract 1 from both sides. So now what I get is s times kss to the alpha minus 1 equals 1 minus delta. So I'm going to subtract out that 1 and stuff, get a nice clean equation here. S times kss to the alpha minus 1 equals delta. Divide both sides by s. I get kss to the alpha minus 1 equals delta over s. Now we're almost done, but I need to do something about that exponent. So what I'm going to do is I'm going to raise both sides to the power of negative 1. What does that do? Well, it is the equivalent of doing 1 over something, right? So if I've got x to the negative 1, that is just equal to 1 over x. So if I raise both sides to the power of negative 1, right, I get 1 over kss to the alpha minus 1, which I can re-express as kss to the 1 minus alpha, and that is equal to s over delta. And if I raise both sides of the equation to the power of 1 over 1 minus alpha, well, I have now perfectly isolated steady state capital. So I've got kss on the left-hand side, and I have s over delta to the power of 1 over 1 minus alpha on the right-hand side. So steady state capital is equal to savings divided by the rate of depreciation to the power of 1 over 1 minus alpha. And remember, alpha is capital's return, capital's share of output. So I now have steady state capital that is being expressed in terms of only exogenous variables, right? Because remember, the endogenous variables were like consumption, investment, output, things like that. The exogenous stuff, right? Well, I've got savings, that's exogenous. I have depreciation, delta, that's exogenous, as well as alpha. So steady state capital is now expressed in terms of the exogenous variables, not the endogenous variables, right? So that's the equation for steady state capital. Let's look at steady state output, right? For steady state output, all I'm going to do is just take equation 4, right, steady state capital, and plug that in for capital into the output equation, right? So YSS equals KSS to the alpha. Well, KSS is S over delta to the power of 1 over 1 minus alpha. So I just plug that in for KSS, and I get YSS equals S over delta to the power of 1 over 1 minus alpha to the power of alpha. If I distribute that alpha, I get something really nice and clean. YSS equals S over delta to the power of alpha over 1 minus alpha. So I got steady state output. Now I want steady state consumption. How do I find steady state consumption? Well, I'll take steady state output and go back to my resource constraint. Because remember, the resource constraint in the steady state was YSS equals CSS plus KSS minus 1 minus delta KSS. And I'm going to plug equation 4 into the resource constraint, and I'm going to get output S over delta to the power of alpha over 1 minus alpha equals CSS plus S over delta to the 1 over 1 minus alpha, remember KSS, minus 1 minus delta times S over delta to the power of 1 over 1 minus alpha. So all I did was anywhere you see a KSS, I just plugged in S over delta to the power of 1 over 1 minus alpha. Work through some stuff, expand some things out. What I get is steady state consumption equals 1 minus S times S over delta to the power of alpha over 1 minus alpha. Now, as a short little aside, let's say I didn't suppress that A term. What would I get? Well, I would get S times A over delta to the power of 1 over 1 minus alpha for steady state capital. And then steady state output would be A times S times A over delta to the power of alpha over 1 minus alpha. Now, when you need to learn these equations and you got to play with them a little bit, equations 7 and 8 are going to be the ones that you're going to be dealing with, right? In that form, that's what you're going to be wanting to play with. So from there, I can get steady state investment, which is just S times steady state output, right? Because S is just the constant fraction that we're saving. Investment is equal to how much we're saving. So investment is S times output. Steady state consumption is 1 minus S times output. So what equations will you need here? Well, you'll need steady state capital, steady state output, steady state consumption, and steady state investment. With these equations here, as long as you know what these equations are, right? You can go, okay, well, if I need steady state capital, this is the equation I'm going to need to use. All right, that's the most that you're going to have to do here. You don't have to derive this stuff. All you need to know is what these equations are and then what they're telling you. So let me get you a little kickstart here on steady state capital. All right, so we've talked about savings, right? That's the rate that you're saving, the savings rate. A, remember, that's sources for technological growth, which then lead to economic growth. Delta is the rate of depreciation. So let's just look at these three terms here. Okay, what would intuitively, right? What do you think would increase capital? Well, if you want to save more, that's going to increase the amount of capital that you have. Okay, I mean, that kind of makes sense, I think. You know, if I want to save more, I'll have more capital, because remember, savings equals investment, and if I'm investing more, it means I'm getting more capital. Okay, so if S were to increase, capital goes up. Awesome. Okay, let's think about that A term. All right, if A goes up, well, if I get technological growth, right, I get something that's driving technological growth in the economy. that goes up, well, I'm probably going to get more capital, aren't I? If, say, let me think of a cool invention that we all know. Okay, let's say Zephram Cochrane invents the warp drive system. Do you think there's going to be more capital involved? I would imagine so. We probably get a lot more space travel going on. So we're going to have a lot more spaceships. And if firms own those spaceships, well, it's going to be more capital. Yeah, so I can see that capital holdings would increase if we get some kind of technological growth. I mean, output's going to be growing. And if output's growing and we're saving a constant fraction of that output, yeah, probably going to see an increase in capital. Okay, so, all right. S makes sense. A makes sense. Let's look at delta, right? Well, delta's in the denominator. So because fractions, remember, if anything in the denominator goes up, right, that numerical value, right, the value of that fraction is going to go down. So if delta gets larger, if depreciation increases, what does that mean for capital? Well, it means capital is going to be falling. Why does it fall? Well, the amount of capital that's falling apart, that's depreciating, delta, increases, which means that the amount of capital that we have on hold, right, that we've got on hand here, is going to be falling. Okay, so S, A, and delta all make sense now in terms of how they behave with the fraction stuff. Okay, well, if that's the case for steady state capital, and capital feeds into output, if something increases steady state capital, it's going to be increasing steady state output as well. If something decreases steady state capital, it's probably going to decrease steady state output. And then from there, remember, output is equal to the sum of consumption and investment. So think a little bit about what would happen to steady state consumption and steady state investment should any of those three variables change, S, A, or delta. And I'm going to leave that to you to just sort of ponder on over the next, 2 days until the following lecture comes out. But from there, we will wrap up talking about the solutions to the Solow growth model. Now, next time, we're going to talk about some applications of the model. Optimal saving strategies, what that means. We're going to talk about transitional dynamics, right? If we move away from a steady state, can we get back to that steady state? Or do we continue to drift further and further and further away from the steady state? And then after that, we'll talk about some growth, right? Can we get growth from the endogenous variables, capital, investment, things like that? Or is it exogenous, such as like a shock to total factor productivity? I kind of want to spoil the surprise, but I'm going to let you sweat it out for like 2 days. And we'll talk about it on Thursday. And then at the end of that, we're really going to learn if it's a good model to use and if there's anything that can be done to improve it, should we need to improve it. And then finally, we'll talk about some real-world applications of the Solow growth model to really understand what it's trying to tell us. Now, that wraps up the lecture for today. More will be coming Thursday, so keep an eye out for that. In the meantime, have a great couple of days, and peace out.